Hey NEET aspirants, welcome back to the extra classes. In today's video, we'll discuss how to study and prepare class 12th physics chapter, electric charges and fields based on NCERT pattern for NEET. This chapter is highly conceptual and forms the foundation for electrostatics. First, let's talk about importance. From electrostatics, NEET usually asks 2 to 3 questions, which means around 8 to 12 marks. Many questions are direct formula-based or simple applications. If you master this chapter, you'll also find the next chapters like Gauss Law, electric potential, and capacitors much easier. Now, what exactly should you study? Focus on Coulomb's law, the expression, vector form, units, and dimensional analysis. Superposition principle, solving multiple charge problems. Electric field, the definition, formula, direction, unit, and examples. Electric field lines, properties, patterns for dipoles, and isolated charges. Then comes electric dipole, the dipole moment, torque, electric field on axial and equatorial positions. Electric flux, its concept and calculation. Now, this is the important one. Gauss' law, statement, conditions, and applications. For example, field due to infinite line charge, plane sheet, and spherical shell. NEET loves Gauss' law applications, don't skip them. Let's get started. Coulomb's law. Coulomb's law states that the electrostatic force of attraction, or repulsion between two stationary point charges, is directly proportional to the product of the charges, and inversely proportional to the square of the distance between them. Here's the mathematical expression, where F is equal to magnitude of electrostatic force. Q1 and Q2 are the magnitudes of two-point charges. R is the distance between the charges. And K is the proportionality constant in vacuum. This is the vector form. Vector form where direction of force depends on the signs of charges. Repulsive for like charges is positive positive or negative negative. And attractor for unlike charges positive negative. With F as the force on charge Q1 due to Q2. And R as the unit vector from Q2 to Q1. Upon applying Newton's law, you get that positive forces and negative forces are equal. This is the value of Coulomb's constant in vacuum or the free space. Here, the SI unit of force F is Newton Nm, the SI unit of charge Q is Coulomb C, hence, K is equal to Newton meter square per Coulomb square. Here are some tips for NEET. Remember that the force acts along the line joining the charges. Medium effect. If charges are in a medium of relative permittivity. And then, superposition principle. The total force on a charge is the vector sum of individual forces due to all other charges. Let us understand the superposition principle. The superposition principle states that the net electrostatic force on any charge, due to a system of multiple other charges, is the vector sum of individual forces exerted by each charge, acting independently of one another. In simpler words, each charge acts on the test charge as if the other charges were absent, and the total, net, force is found by adding all those forces vectorially. Let us see the mathematical expression. If a charge Q is influenced by n other charges Q1, Q2 or Qn, and the force on Q due to an individual charge Qi, is Fi, then net force is the summation of all the forces, where each individual force is given by Coulomb's law. Hence, the mathematical expression becomes this. Here are a few neat tips on superposition principle. The forces are vectors. You must consider both magnitude and direction. Forces obey vector addition, not scalar addition. The principle is linear, meaning the effects of multiple charges add linearly and no interaction terms. And superposition principle applies to both magnitude of force and electric field. Let's look into one example. If three charges, positive Q1, positive Q2, and positive Q3 are placed linearly on a straight line, then the net force on the middle charge positive Q2 is the algebraic sum. This is because they act along the same line. Finally, the same principle applies to electric field vectors. This is extremely useful in NEET for questions involving square or triangle charge arrangements, midpoints or symmetric positions, and resultant electric field at a point. Let us now study electric field. The electric field at a point is the electrostatic force experienced by a unit positive test charge placed at that point. It represents the influence of a charge in the surrounding space, that is, how strongly it can affect other charges placed nearby. Let's look into the formula for electric charge. For a point charge q at distance r, this is the formula for electric charge, where epsilon naught or epsilon 0 is the permittivity of free space, also known as the electric constant. Q is the source charge, and r is the distance from the charge. And this is the vector form, where r hat is the unit vector from the source charge to the point of observation. The direction of the electric charge depends on the sign of q, and, for positive q, the field is outward, that is away from the charge. For negative q, field is inward, towards the charge. Please memorize following SI units and dimension formulas. Let's look into some of the important relations. First, relation with the force on charge q, in electric field E. Then, the relation with potential, where electric field is the negative gradient of electric potential. And finally, in a medium of relative permittivity with epsilon r. Here's an example. Field due to two equal and opposite charges, that is electric dipole. At an axial point it is represented with 2p. And, at an equatorial point it is represented with single p. The direction is along the axis, that is, from positive to negative charge. Here are important NEET tips. Electric field is a vector quantity, hence direction matters. For multiple charges, use the superposition principle. Electric field lines never cross each other. And, field lines originate from positive and terminate on negative charges. Let us study electric field lines. Electric field lines, or lines of force, are imaginary lines drawn in an electric field such that the tangent at any point on the line gives the direction of the electric field at that point. They help visualize magnitude and direction of electric fields in space. The electric field lines can be represented in following ways. The density or the closeness of lines represents the strength of the field. Closer the lines, stronger the field. And, farther the lines, weaker the field. Then, the arrows on the lines indicate direction. Outward, from positive charges. And, inward, toward negative charges. Understand the properties of electric field lines very carefully. 1. Electric field lines begin and end on charges. 2. They don't intersect each other. 3. Closer the lines, stronger the field. 4. Electric field lines are perpendicular to surface of conductor. 5. Never form closed loops, because electrostatic field is non-curling. 6. Number of lines are directly proportional to the magnitude of charge. 7. These lines bend in a medium. And 8. Direction of force. A positive test charge moves along field lines, a negative charge moves opposite to them. Let's understand the field line patterns. For an isolated positive charge, lines radiate outward uniformly in all directions. Field is spherically symmetric, and lines are equally spaced on a spherical surface. Direction is away from the charge. For an isolated negative charge, lines converge inward symmetrically toward the charge. Strength increases as we move closer, and direction is toward the charge. Whereas, for an electric dipole, with positive and negative charge separated by 2a, lines originate from positive q, and terminate on negative q. Lines are denser near the charges and stronger field near the ends. The axis joining charges is the dipole axis. At large distances, the pattern becomes similar to that of a single charge, but weaker field, where field is inversely proportional to r cube. Electric field is represented by the number of lines per unit area. Here are few important NEET tips. No crossing of field lines means unique direction of field at any point. Equipotential surfaces are always perpendicular to field lines. Parallel uniform field lines are equally spaced and parallel, for example, between two oppositely charged plates. Field inside a conductor is zero, so no lines exist inside it. An electric dipole is a system of two equal and opposite charges, positive q and negative q, separated by a small distance, 2a. For example, water. H2O molecule acts like a natural dipole. The electric dipole moment, P, is a vector quantity defined as P equals Q into 2A, where Q is magnitude of one charge, 2A is the separation between the charges, and direction of P is from negative Q to positive Q. The SI unit is Coulomb meter. Let us understand torque on an electric dipole in uniform electric field. when a dipole is placed in a uniform electric field E, making an angle theta with P, then tau is equal to P A sin theta, where direction is perpendicular to the plane of P and E, and torque tends to align the dipole along the direction of the electric field. There are certain special cases when theta varies from 0 to 180 degrees, and these are stable equilibrium, maximum torque, and unstable equilibrium. Let us understand potential energy of a dipole in uniform electric field. U is equal to negative P A cos theta. It is stable when theta is 0, and it is unstable when theta is 180. What happens to the electric field at dipole? Let's understand. At axial point, or on the dipole axis, direction is along dipole moment, P. Field is stronger here. At equatorial point, or perpendicular bisector of the dipole, direction is opposite to dipole moment. Field is weaker compared to the axial point. Ratio of field strengths is 1:2 between axial and equatorial point. The general expression for vector form of electric field due to a dipole is this. Here are few neat tips to remember. Torque is equal to 0 when dipole is aligned or opposite to field direction. Field strength decreases with cube of distance. Axial field is twice the equatorial field in magnitude. Net charge on a dipole is 0, but electric field is non-zero. Let's study electric flux, or Phi. Electric flux represents the total number of electric field lines passing through a given surface. It gives a measure of how strongly the electric field penetrates a surface. It is a scalar quantity, though it depends on the angle between the electric field and the surface normal. If a uniform electric field E passes through a plane surface of area A, and theta is the angle between the field and the normal to the surface, then phi is equal to E A cos theta, where phi is electric flux, E is the magnitude of the electric field, A is the area of the surface, and theta is the angle between E and the surface normal. The vector form of the electric flux through any surface, S, is given by the surface integral. Here, dA is infinitesimal area vector, perpendicular to the surface. And E dot dA is E dA cos theta. This is the expression, unit, and the dimensional formula for electric flux. There are several interpretations to be remembered. More field lines means greater flux. If the surface is perpendicular to the field, then it means maximum flux. If the surface is parallel to the field, then no flux passes. And negative flux means the field lines enter the surface or into the plane. And here we are on the most important topic of this chapter, Gauss's law. It states that the total electric flux through a closed surface is equal to 1 upon epsilon naught times the net charge enclosed within the surface. Here's the expression, where integral S is the closed surface integral over the surface S. A is the electric field vector. A is the infinitesimal area vector, normal to the surface. Q is the total charge enclosed. And epsilon naught is the 8.854 into 10 power minus 12 Coulomb square per Newton meter square. Gauss's law relates the electric field to the distribution of electric charges producing it. It helps calculate E for highly symmetric charge distributions like spherical, cylindrical, and planar. These are some of the conditions for applying Gauss's law. Spherical symmetry, with example as point charge and uniformly charged sphere. Cylindrical symmetry, with example as infinite line of charge. And planar symmetry, with example as infinite sheet of charge. There are several important concepts to remember. Only enclosed charge contributes to flux. Charges outside the surface have no effect on net flux, that is, their field lines enter and exit symmetrically. Flux depends on net enclosed charge, not on shape, size of surface. The same total flux passes through any closed surface, enclosing the same charge. If no charge enclosed, that is Q, is 0, then field may exist, but total flux through closed surface is 0. Let's see the applications of Gauss's law. First, electric field due to a point charge. Consider a point charge positive Q at the center of a spherical Gaussian surface of radius r. Then, the result is similar to Coulomb's law. Second, electric field due to an infinite line of charge. with linear charge density as lambda, and, for a cylindrical Gaussian surface of radius, r, and length, l. The field is inversely proportional to r. Third, electric field due to an infinite plane sheet of charge, with surface charge density as sigma. Use of a pillbox Gaussian surface results that the field is uniform and independent of distance. Here are some neat tips. Gauss' law applies to static electric fields only. It's a direct consequence of Coulomb's inverse square law. It gives qualitative and quantitative field strength in symmetric systems. The shape of Gaussian surface is chosen to match symmetry, so that E is constant over it. For non-symmetric charge distributions, Gauss' law holds true, but is not practical for finding E. Here's the smart way to study. Keep a formula sheet for quick revision. For conceptual clarity, draw diagrams for field lines in Flux. They often ask diagram-based questions. Practice NCERT solved examples and back exercise problems. Many NEET questions are directly picked from these. And remember, physics isn't just reading, it's about practicing numericals. Solve at least 40 to 50 MCQs per topic. These questions are available on extra classes. Most students make these mistakes. Confusing scalar versus vector quantities. Always check direction in vector problems. Misusing Gauss' law. It only works for high symmetry situations. Ignoring units and dimensions. Sometimes NEET asks direct unit questions. Avoid these pitfalls and your accuracy will improve. So that's how you should prepare electric charges and fields for NEET. Stick to NCERT, practice previous year questions from extra classes, and revise formulas regularly. If you found this video useful, hit the like button, share it with fellow NEET aspirants, and subscribe for more NEET physics, chemistry, and biology strategies. All the best, future doctors. Join extra classes for free today. Use the promo code in the description.